This meeting is being recorded.
In problem 24 from chapter 15, we are given the molecular formula for a compound here. We are told that it produces a proton NMR spectrum that only has two signals, and both of these are singlets. So the first signal appears at 3.9 ppm, and we have a relative integration of 79, and then we have a second signal here with a relative integration of 52. So with only this information, we're asked to identify the structure of this compound. So what we can do is first we can begin with the calculating the hydrogen deficiency index, the HDI. If you remember, this was in section 14.16. So because we're given that molecular formula here, we can do that. So the formula 1/2 2 times 10, so we have 20 plus 2 minus our hydrogens. We ignore the oxygens, and we don't have any halogens or nitrogen to consider. So this is our formula here. So we have 22 minus 10, 12 divided by 2. We have an HDI of 6. So something you should take notice to is that an HDI equal to 4 commonly can represent a benzene ring. So we likely have that structure plus 2 other additional degrees of unsaturation in this compound. Then in a second step here, we can look at the integration of these signals and find a ratio. So we have our first signal has a relative integration of 79. The second has that of 52. So we'll divide each by our lower value here. Right, so we have 52 over 52 gives us 1, and 79 over 52 gives us about 1.5. So we have this 1.5 to 1 ratio. And since we have 10 protons, this number then must correspond to 4 protons to 6 protons, right? So 6 to 4 is the same as this 1.5 to 1 ratio here. So let's take a look at what other considerations. Let's look at each of these signals individually now. So we have one signal at approximately 3.9. So 2, 3, and we have, we'll go a little bit further. So here's our singlet at 8.1, and then we have our other singlet 1, 2, 3.9. All right, so we have our two signals, the one at 3.9, the other at we'll say 8.1 over here. So what can these mean? The signal at 8.1 is significantly downfield. So we could say that this probably represents aromatic protons. So that reinforces our HDI of 4 being representative of a benzene ring. And this signal downfield would then have an integration of 4, or since it does have that integration of 4, right, because we're told that it has the integration value of 52, so that must correspond to 4 protons here. That would make sense that we have this structure so far. All right, so we have our benzene ring here, and it has these 4 protons giving rise to that signal at 8.1. And then we still have those other 2 degrees of unsaturation to consider. So when we think about the other signal, the other singlet that has an integration of 6, this could represent 2 methyl groups, right? So 2 symmetric methyl groups to give us those 6 protons with that singlet integration, and therefore they would not have any neighbors And this chemical shift that we see around 3.9, this would be consistent with methyl groups being attached to the oxygen of an ether, or actually the oxygen of an ester, right? Because we need a shift of about 3.0. So if we continue piecing together our structure, we think that we might have a di-substituted ring here. And we back calculate from our shift of 0.9 ppm. We add, say we have an ester here. This would be an additional 3.0 ppm. So we can kind of create these pieces and then form our di-substituted benzene ring here. And this would also account for those additional 2 degrees of unsaturation that we see with our compound. So now we go back and we double check and make sure that all the information correlates with the structure that we've drawn. So again, we have 4 protons that would integrate around 8.1. So those are our 4 aromatic protons shown here. And that would be a singlet. And then we confirm that our 6 integration protons here, so these 2 methyl groups, they are alpha to an oxygen of an ester, so they should produce that signal around 3.9. And due to symmetry of this compound, we confirm we should only see two singlets, both at these shift values.